So we are very, very happy to have Sujoy give a talk today. He is on faculty of IIT Bombay and also a visiting fellow at the Department of Math at London School of Economics. He had got his degree from Ben Gurion University in Israel, working under Pascarmi, and then he had a few postdoc positions at Technical University of Vienna and at ULB Brussels. And right now, I would rather listen to him talk than continue this, but we are extremely happy to have you speak. Please go ahead.
Uh, Thanks, Boris, for the nice introduction, and thanks the organizers for giving me the opportunity to talk at this seminar. Hello, everyone, and thank you for attending my talk. So I plan to talk about a theme of results that we have been discussing for last 1 year. So it broadly comes under the theme of fast, static, and dynamic approximation algorithms for various classes of geometric optimization problems. And everything that I will talk today, this is a joint work with Timothy Chan from UIUC, and Timothy said he will also join in few minutes. So let me begin with saying that objects play a very pivotal role in our existence, and we are surrounded by objects in our ambient space around us. They are in different forms and shapes, for example, axis parallel, orthogonal shapes, or different kinds of polygons, convex, non-convex shapes, different kinds of curves and straight lines, line segments, or balls, spheres, etc. And as Kepler said that wherever there is matter, there is geometry. So I don't have to motivate geometry to this audience, but what I want to highlight is that inside geometry, the study of different classes of objects play a very crucial and central theme. So not only that they are mathematically interesting and robust classes of objects, but they also play a pivotal role in our understanding of various classes of optimization problems. Just to name a few areas like resource allocation, data mining, geospatial information, robotics, or wireless sensor networks, visualization, different classes of packing and covering problems or routings, etc. So let me define a class of graphs, which are called the intersection graphs of objects. So in this setup, we have a set of vertices, which are a set of objects. And if two objects intersect, then there is an edge connecting them in the corresponding intersection graph. So for example, here we have a set of disks in the plane, and when two disks overlap, then there is an edge between them. So we are interested in various classes of optimization problems like classical optimization questions, namely a minimum piercing set, maximum independent set, minimum vertex cover, and maximum cardinality matching. Now, as it turns out that almost all of them are already computationally interactable for most natural families of geometric objects, and even for most simple classes of geometric objects like unit square intersection graphs or unit disk intersection graphs. Matching, of course, is polynomial time solvable problem, but there the goal is quite different. There one wants faster solutions. So for all of these problems over the decades, like different kinds of approximation and exact algorithms have been developed. So the broad theme that we have been interested in, due to the rise of like this large scale data that we feed in different kinds of optimization problems, is that Can we actually design algorithms which runs in almost near linear time, near linear in the scale of the input, of course. And more importantly, also, like we are dealing with inputs which are no longer static. They are changing over a period of time, in a sense that the input, like a portion of the input is inserted or deleted over a sequence of updates. And the goal is to maintain efficient solutions, and not to just compute at one particular point of time, but to maintain these solutions over a period of dynamic updates, let's say through insertion or deletions. So with these two broad theme in mind, so let me dig now deeper into the questions that we are interested in. So the first problem that I want to talk today is a very natural geometric optimization question, is called minimum piercing set. So we have a set of n geometric objects in d-dimensional Euclidean space. So in this example, we have a set of disks in the plane. And our objective is to find a piercing set, which is a set of points of smallest size that stabs or pierces all the objects. So piercing set is mathematically a natural question, and also it has applications in facility locations or wireless sensor networks. Theoretically, it's also interesting because it can be viewed as a continuous version of the heating set problem. And we know that the heating set problem in turn is connected to the set cover question, because the geometric heating set actually corresponds to the geometric set cover in the dual range space. So this is a problem of interest for computational geometry community for many years. So we know that uh, from the greedy algorithm of the set cover, and also for heating set, that there exists a log factor approximation for any family of piercing set with constant description complexity. So over the years, the objective has been to get better and better approximation algorithms. For example, for near equal size fat objects in d-dimensional Euclidean space, Hotchpam and Mass showed that there is a 1 plus epsilon approximation with the running time into the order 1 by epsilon to the d. Roughly, the idea is to use the shifted grid mechanism. So greedy already gives a constant factor for fat objects in d dimension. So if one does a naive implementation, this is roughly quadratic, but if one does a little bit smarter implementation, this can be like n polylog n. So this is fast, but then the approximation factor is somewhat large. Now, for arbitrary size fat objects, there is a separator-based algorithm by Chan that also achieves the approximation factor 1 plus epsilon with the time into the order 1 by epsilon to the d. And recently, last year in SODA 24, Agarwal, Harpeled, Roy Chaudhuri, and Sintos, they showed that there is a log-log opt approximation for arbitrary boxes in D dimension, which runs roughly in n to the d by 2. And their technique primarily use the multiplicative weight update and along with the net mechanism, etc. So our question is that, can we get near linear time sub-logarithmic approximation algorithm for minimum piercing set? And also, can we somehow come up with one solution which can be sort of dynamized, and can we get a dynamic algorithm with sublinear update time as a byproduct of this? So it turns out,
Sorry,
yes.
Sujoy, I just have a question.
Yeah.
So on the previous slide, so how bad is the order one in the second row?
I don't remember exact factor actually.
Okay, cool, thanks.
So yeah, so so our first result is to answer this question of the near linear sub-logarithmic approximation algorithm for MPS. So for boxes in RD, we get a log opt approximation, which runs roughly in n to the 1 plus delta for some constant delta greater than 0. So this, as you can see, is a major improvement in terms of the running time. The previous running time of Agarwal et al. Was n to the d by 2. So for fat objects in RD, for any constant D, assuming, of course, constant description complexity, we get a constant factor approximation running in n to the 1 plus delta delta time. So it turns out that we kind of get almost like lossless dynamization. So for boxes, we can maintain similar factors asymptotically, of course, like log opt approximation with n to the delta update time. And for fat objects, we can maintain constant factor with n to the delta amortized update time. So I want to highlight one point here is that like one recipe for getting dynamic algorithms has always been like you get a static algorithm and then try to dynamize it at the expense of losing something in the approximation factor, because typically the goal is to get like a sublinear update time. And but it turns out that here in this problem, like we don't really have to lose much. And one more point also I want to highlight that in the typical dynamic graph algorithms regime, the update model is edge insertion and deletion. Unlike in the geometric setting, we can actually talk about vertex updates, which is not possible in the graph model because of the degree barrier. So let me describe briefly the first result, and then I will move to other questions. So the first result is the minimum piercing set for boxes. So I'm going to first consider a very, very special instance. This can be thought of a different this can be approached through many very different ways. Like it can be thought of creating some sort of a kernel of the instance, or looking at a special instance. But so we are going to consider a special instance first, which can be solved by rounding the input boxes. So let's say that we are given a set of roughly order B axis aligned hyperplanes. This parameter B, we are going to set it later. So let's say that we have this set order B of axis aligned hyperplanes in RD. And let's say that we have a set of n axis aligned boxes, and each box is tapped by at least one of the hyperplane, which is orthogonal to the kth axis for every k. So in that case, we can compute log opt approximation of the minimum piercing set in n plus b to the order 1 time. And it also can be made dynamic. It supports insertion and deletion in b to the order 1 time. So here roughly the arrangement looks like. So what basically these axis aligned hyperplanes will do is that they form a non-uniform grid with roughly B to the D many grid cells. Now there will be multiple there will be multiple boxes which are going to intersect or contain a same subset of the grid points. And we are going to place them in the same class if they intersect the same subset of grid points, which means that roughly we will get B to the 2D many classes. And let's say that we create a special subset S hat by keeping one representative from each of these classes. So we have this grid partition, we break the whole instance into a smaller set of classes, and from each of this class, we are going to keep only one representative. Therefore, the cardinality of this representative class is roughly ordered B to the 2D. Okay. So at this point, we have multiple options to just finish this instance, because if we are in the dimension 2 or 3, we can use the epsilon net algorithm of Aronov, Ezra, and Sharir. If we are in dimension d greater equal to 4, then we can actually use the Agarwal et al.'s algorithm. So in any case, we will be able to get the order log opt in b to the order 1 time. So let's say that P is the return piercing set, and for each point, we are going to add all the 2 to the D corner of the grid cell, which is containing this point P to this actual piercing set that we are going to report. So let's look at that, why this is a valid solution to take in the first place. So the claim is that P prime, which is formed by taking all the grid points around this point P, which 2 to the D many points around this point P, is a piercing set of this set S. Now, like here in this example, notice that from the class that S hat belongs, this red rectangle or the red box. So there has to be something that is piercing this particular box. So in this case, let's say there is this red point, which is actually piercing this red box. Now, all the other boxes which are not chosen in the representative class, the reason they are not chosen because they are in the same class with S hat, which means if I choose like this 4 corner points around this point P, this is definitely going to hit all of them, because this is just by the definition of the representative classes. At this point, insertion and deletions are fairly trivial because this can be just achieved by simply maintaining linked list for each of these classes. And then every time there is a problem, we just rerun the Agarwal et al. But of course, this is a special instance, and this is not the whole instance. Now, let's come back to the global instance. So what we are going to do is that we will combine this lemma with some sort of a B-array version of the divide and conquer mechanism. So the main theorem is that, so we have these n-axis aligned boxes. We can compute the order 1 by delta to the D log opt approximation to MPS for S into the 1 plus order delta time. And it also supports insertion and deletion into the order delta amortized time. So, so let me define the type J problem. So for different values of J between 0 to D, by assuming that this instance S is tabbable by order B hyperplanes orthogonal to the kth axis for every k between 1 to J. Now, the original problem that we are starting with, this is a type 0 problem, and the type D problem is something that I have already described in the previous lemma. So what we are going to do is to solve all the other type J problem, which is smaller than D. We are going to build this B array tree. So pick B minus 1 hyperplanes, which is orthogonal to the J plus 1th axis, divide the space into B many slabs, and each of these is going to contain roughly ordered n by B many corner points. So we are going to store the boxes in S stabbed by this B minus 1 dividing hyperplanes at the root. So we recursively build this subtree for the subsets of order n by B boxes in S contained in each of the B slabs. And now for each of the order log n many levels of the tree, we compute the piercing set for the subset of all boxes stored at that level. And we are done. Because we do it for each of these node, we take the sum, and then for each node, this is going to be a type J plus 1 problem. That's it. So the approximation factor, so for a type J, this satisfies the recurrence that f of J is at most order log Bn times f of J plus 1. And so therefore, the overall approximation factor is log Bn to the D times log opt. And the running time, so observe that in the type J problem, each box is stored in one node of the tree and therefore assigned to one type J plus 1 problem. And since the running time of each of the type D problem, as shown in the lemma, that it is going to take like B to the order 1, so the overall running time is going to be B to the order 1 times N. So the dynamic is a fairly easy extension at this point. So whenever we are going to insert or delete a box in the type J problem, we will insert or delete the box in one type J plus 1 problem. And then so the update time is simply B to the order 1 by the lemma. and the update time for the original type 0 problem is going to be order b to the order 1. Of course, there is one small technical issue which I'm hiding, which is the typical tree balancing stuff, because every time for each of the subtree with n boxes, each child should actually have roughly order n by b many corner points. But one can use like the standard weight balancing scheme or rebuilding the subtree after it encounters n by b many updates. Finally, we set this b to be n to the delta, and this gives us all the bounds that we claimed. So the first remark is that this log-log opt approximation for piercing boxes, if there is a better approximation algorithm, let's say, and it doesn't have to be fast actually. If there is just a better approximation algorithm, then putting in our framework, we can already get a near linear solution with a better approximation factor. So this MW-based approach by Agarwal et al. Is efficient for small opt, but this rounding mechanism that we have described, this is somewhat general, and it's not related to any LP or MW type mechanism. But in all fairness, we incur some extra constant factor, which is like related to this 1 over delta to the d, which is okay like as a constant blow up asymptotically. But if one cares about this, then like the Agarwal et al.'s factor was slightly better. So we give another static algorithm, which I am not describing here, with n polylog n running time with approximation log-log opt using Monte Carlo randomization. But this actually doesn't compute the actual piercing set. It just computes the value of this. Yeah. And also dynamic algorithms can be sort of de-amortized using the standard techniques on weight balancing trees. Okay, so let me move to the next problem, which is the maximum independent set problem. And so there. Okay. So in the maximum independent set problem, we have a set of n geometric objects in d-dimensional space again. Like here, we have a set of rectangles, and you will see that why the example is chosen for rectangles now. And sorry. So the goal is to choose a maximum cardinality subset of independent objects. So maximum independent set is one of the most extensively studied problem in combinatorial optimization and theoretical computer science. Since the size of maximum independent set is always at most the size of minimum piercing set, for near equal size fat objects, there is this shifted grid mechanism by Hotchpam and Mass. This gives a PTAS. For fat objects, the greedy gives like a constant factor. So in this case, I know that at least for disks, I think the factor is roughly 6 or something around that. So there are several polynomial time approximation schemes for arbitrary fat objects, including the pseudo disks with the running time n to the order 1 by epsilon to the d, or n to the order 1 by epsilon to the d minus 1, which have been found via different types of techniques, like to name a few, like shifted quadtrees or geometric separators. And then Chan and Harpelet in their seminal work had this PTAS using local search for arbitrary fat objects. So the case of rectangles has been particularly fascinating for independent set problems. So we know from 90s that there is a log factor approximation with n log n time algorithm via the standard binary divide and conquer approach. So in 2009, it was shown that there is a log-log-n approximation by rounding the LP solution using somewhat intricate analysis. Then Andy and others, they showed there is a QPTAS by using separators and dynamic programming. And the first major breakthrough after nearly 3 decades by Joe, and he gave a constant factor approximation for this problem. And subsequently, Galvez et al. Gave this approximation factor to be 2 plus epsilon. So the question that Joe asked in his work is that can the running time of a constant factor approximation algorithm be improved significantly? So this is the question that we are interested in first in the independent set problem. So what we show is that for rectangles in the plane, there is a constant factor approximation with the running time n to the 1 plus delta. So this improves the running time significantly. And also for fat objects of constant description complexity, we give a order 1 approximation in n to the 1 plus delta time. So next, the question is about dynamization. So the question is that does there exist a constant factor approximation with sublinear update time for rectangles, or say like n to the 0.1 update time for fat objects in RD for d greater or equal to 3? So it also turns out to be yes, it is possible to maintain a constant factor approximation. Actually, like originally, this is the problem that I was interested in, to get constant factor for dynamic rectangles or fat objects. But yeah, so like the typical approach is to go via the static one. So and then also it generalizes to the weighted case, but for the weighted rectangle case, the static and dynamic algorithms that we propose have the same running time, but it will have the approximation factor log n. And this is the best known approximation anyway, like so for the weighted problem, we don't have a constant factor approximation. Okay, so let me briefly describe this method. So the general framework is somewhat very similar, like the one that we have used for the minimum piercing set. The only key difference is that in case of the piercing set, the budget was much higher because we were playing at the regime of log opt. But now our budget is constant factor, so we cannot really afford to be sloppy in our charging scheme somehow. So again, I'll first focus on a specific sub instance, and then I'll try to generalize this. So let's say that we have a set of order B horizontal or vertical lines, and each input rectangle is tapped by at least one horizontal or one vertical line. So for the unweighted case, we can get a constant factor in n plus b to the order 1 time. And it also supports insertion and deletion in b to the order 1 time. And for the weighted case, we can do the same, but now with the log b. Approximation to the maximum weight independent set. Okay, so this is again, we are back in the arrangement. So we have now these horizontal or vertical lines, and so we define the equivalent classes based on the rectangles intersecting the subset of these grid points. And from each of these class, we are going to choose again one representative. Now, if it is the weighted case, then we are going to choose the largest representative. For the unweighted case, it doesn't matter. So we can just choose anyone. So for the unweighted case, one can simply apply Mitchell's algorithm to get a constant factor approximation. However, for the weighted case, so there is another breakthrough by Parinia and Bartos from SODA 21, where they gave a log opt approximation for the independent set. And I should also point it out that in that paper, they also give answer to one of the another important open question, which is about the chromatic number of rectangle intersection graph, which was earlier omega squared. They got it down to omega log omega, which is also a very nice improvement. So so now the approximation factor is that, let's say that this I star is an optimum independent set. And now for each rectangle S, let's say this S cap is this representative element in the S class. So the claim is that we are going to form the independent set of cardinality, which is constant times the cardinality of I star in the unweighted case, and constant times the weight of I star in the weighted case. So basically the argument goes as follows. So what we want to show is that this arrangement that we are currently dealing with, this has maximum depth at most 4. Because if there is a point P that lies inside S hat, like in this case here, then S intersects the grid cell containing this point P. So S contains one of the 4 corners, and at most there will be 4 rectangles which are going to satisfy this situation. And then we can use the Parinia and Barthos's lemma, which says that every arrangement that has the maximum depth delta, this is delta log delta colorable. So and then we are pretty much done, because in this case you can just take the largest cardinality or the weighted color class as the independent set of S hat. So the insertion and deletions again can be simply handled by linked list per class in the unweighted case, and for weighted case priority queue to maintain the largest weight element per class. And we also gave another proof via probabilistic argument, which does not use the coloring of the arrangement. But I want to point it out that this alternate argument, this does not actually give an algorithm explicitly. So for the algorithm, we still take Parenias and Barthos's algorithm. So I'm not going into the proof for this, because the proof technique is somewhat similar to the one that I described for a minimum piercing set. So for the approximation for the type J problem, which satisfies the recurrence that is order B or order log Bn times f of J plus 1. And so the overall approximation factor is going to be log of Bn to the D times log B. And the analysis of the running time is similar like before. So this randomized variant also works in the independent set case, and we can get a constant factor approximation for in running in order n polylog n running time. But again, this does not compute the actual independent set. This only computes the value of the independent set. And also, like similar, like the piercing case, any improvement on the approximation factor for any polynomial time algorithms for weighted or unweighted case will automatically give us like faster static and dynamic algorithms for any constant dimension D. Okay, so actually I want to take a little bit of a detour at this point and tell a little bit about our another result, but in the similar on the similar topic actually. So so let me focus a little bit more on the dynamic aspect of this question, which I said that this was the problem that I was interested in the beginning. So the dynamic version of this independent set problem, it started due to its motivation in scheduling and geospatial information projections and this kind of applications. But it has been like quite extensively studied now theoretically in the last few years. So for example, for intervals, which is the simplest, most geometric objects, we know that it's possible that one can maintain a 1 plus epsilon approximate solution in like polylog. I actually like a log n over epsilon update time. So for squares, we knew from 21 that this is it's possible to maintain constant factor in polylog amortized update time. For arbitrary radii disks, we know from sausage 24 that there is a constant factor approximation in polylog expected amortized update time. And based on a lower bound for the static case by Daniel Marks, one can show a reduction that if one wants to maintain a 1 plus epsilon approximate solution for unit disks, let's say in the plane, it's not possible to go sublinear. So the point is that like 1 plus epsilon maintenance regime is gone for any kinds of objects beyond interval. So the goal is always like to do like constant factor maintenance if one wants like a sublinear update time. So here actually we want to be a little bit more, we want to squeeze this a little bit more, and we want to say that, okay, so not just sublinear, can you get us to polylog? Because like, if you notice that for the case of arbitrary radii disks, so from sausage last year, so we had a constant factor approximation with polylog expected amortized update time. But the analysis was like a fairly complicated and long. So we are interested in finding a simple solution with constant factor approximation with polylog amortized update time. So this is a work also with Timothy in SOSA this year. So we give a new dynamic constant factor approximation for the for this independent set problem for the case of disks in the plane with polylog amortized update time. So I want to highlight that this whole algorithm and the analysis is like within 5 pages, which actually significantly simplifies the previous algorithm from Sausage 25. And also along the way, it improves the update time by shaving some log factor in the update time. So this is even faster. It avoids the randomization completely. So this is better in that sense. So for hypercubes in RD, for any constant D, also we get a dynamic constant factor approximation in log n amortized update time. So this substantially reduces the number of log factors of the previous method by Monica and Andy and others, and also one of our previous work from order D all the way to 1. And as a byproduct of this, we also get a new constant factor approximation for the arbitrary fat objects in RD running in order n log n time. This is slightly faster than the previous things that I have described, although I didn't talk about the arbitrary fat objects. But in all fairness, like that work could handle the weighted setting and so on, but this is like really the unweighted setup. And like pretty much everything that I describe here, the same approaches work also for the piercing set as well. So Boris, how much time do I have?
Well, you have at least 10, 15 minutes.
Oh,
15
okay.
minutes, definitely.
Okay, thanks. Yeah, so I'll just very briefly describe this and then go to the conclusion. So so for fat objects, like let's say that we for any hypercube there exist so there are many different ways to define fatness, and one of the ways to define fatness is that for any hypercube there exist constant many points which pierces all the objects that intersect this hypercube B and have L infinity diameter, at least diameter infinity of B. So assume also that each object has constant description complexity, and assume that we have a data structure which tells that if an object is inside a query object or outside a query object. Under this pre-processing time, which we are going to call like P0N, amortized update time, which we will call U0N, and query time, which we will call Q0N. So quadtree, I don't need to define this, but it's for completeness, it's just a recursive partitioning of the space into like quadrants, and until like each of the cell has like some limited number of objects in it. And we want some, so the main thing that we don't like basically in this question is that like there is some meta quadtree partition, and all of these objects which are content inside some quadtree cell, they are somehow good because like we are going to handle them when we are handling them. But then there are objects which are like overlapping at the boundary, and they are problematic because like in the charging mechanism, they can be charged in multiple ways, like because multiple cells are like sharing the boundary, and then this could be problematic. So we want some sort of a goodness factor uh, to be to be maintained, and we call that an object is C0 good if S is contained in a quadtree box with the diameter at most like a C0 after like C0 blow up. So this goodness is desirable because these good fat objects intersecting the boundary of a quadtree box must have this L infinity diameter, at least like diameter infinity of B over C0. So it can be pierced by constant many points. Okay, so how do we achieve this goodness? This can be achieved by the so-called shifting lemma. So you take this whole arrangement and do this shifting, and this can guarantee that this goodness can be achieved. And of course, like the quadtree doesn't have to be balanced because it can happen that there is like a one long path of objects. Every other like quadrants are fairly empty, so it's like you keep going in one direction. So a quadtree cell is defined as either a quadtree box or the difference of an outer quadtree box and an inner quadtree box. So our broad goal is to generate a structure which is some sort of an augmented version of the shifted balanced quadtrees. So there is an old result by from 1998 which says that if you have n points inside a quadtree cell, then we can decompose into constant many disjoint quadtree subcells such that each subcell contains at most alpha n many points for some constant alpha less than 1 in order n time. So so then in the lemma, we show that we can maintain this augmented balanced quadtree of n objects in constant dimension under insertion and deletion in roughly time order U0n plus P0n by n log n plus log square n amortized after time. And to insert and delete, basically we are going to find the unique cell by descending along the path of the tree in log n time and update in order U0n time. So to ensure the balancing factor, whenever the number of cells in the child exceeds like some threshold, let's say alpha plus delta times the number of centers in the parent cell, we are going to rebuild at the parent and then charge all of this in an amortized way. So this is the algorithm basically. So given these augmented balanced quadtrees, it's possible to compute this approximate maximum independent set from scratch in time sensitive to opt. So the quadtree suggests some sort of a simple divide and conquer mechanism, but if we really just go only by the quadtree mechanism, then you could actually lose log factor because you're gaining this in every level of the quadtree, even if it is a balanced quadtree. So the key idea that saves us is that like we skip over the paths of all degree 1 nodes during this recursion. So I don't want to describe much more on this. So I'll just keep this. I think this is enough that as the generic idea of the algorithm. So let me talk about this specific application. So for disks, we can show that it's possible to maintain like constant factor approximation using this mechanism and some extra stuff in polylog amortized update time. And also for fat boxes, it is possible to maintain the constant factor approximation in order log n amortized update time. So the approximation of our algorithm is somewhat in the order of like order d to the d, but it can be lowered to order 1 to the d. So for constant d, this is still constant. And so for the static case for n fat objects of constant description complexity, we can also get a constant factor approximation for maximum independent set in order n log n time. So now the remaining time that I have, I just want to highlight the results that we have for vertex cover and matching, and I will not go into the details of these results. So the vertex cover problem is like, again, one of the most well-studied questions in optimization. So we have an undirected graph where a subset of vertices is vertex cover if every edge has at least one endpoint in this subset. So the minimum vertex cover asks for a vertex cover of minimum cardinality. So in the exact setting, this is actually a complement problem to the independent set. So we know that there is a p-task for minimum vertex cover for fat objects in d dimension. For rectangles in the plane, there is a 3/2 plus epsilon approximation. Of course, for vertex cover on general graph, we know this whole story of unique game conjectures and so on. So for geometric objects, of course, we know much better approximation factors. So for instance, due to Harpeleth, we know there is a quasi p-task for minimum vertex cover for polygons. Now we know there is a slightly better than two-factor approximation for string graphs. The question is that does there exist like any near linear time better than two approximation for minimum vertex cover, and can we sort of also get like dynamic algorithms with sublinear update time for what families of objects, of course. So we show that for rectangles, one can get 1.5 plus epsilon approximation in polylog n time. For disks and fat boxes, we actually speed up the previous p-tasks, and currently they run in polylog n time. Also, it holds for bichromatic disks and fat boxes. For dynamic results for rectangles, we can maintain this 1.5 plus epsilon approximation in order polylog n update time. And for disks and fat boxes, we can maintain 1 plus epsilon approximation with order polylog n amortized update time. And I want to highlight that, so this 1 plus epsilon maintenance is somewhat rare in dynamic geometric optimization under vertex updates. As you have seen already for independent set, for instance, it is not possible. And I mean, the reason is not just in the only exclusively in the dynamic regime. This is already we can see in the static case, like there is no efficient polynomial time approximation scheme or the others. So, but for vertex cover, one can maintain 1 plus epsilon approximation. So it's not possible for independent set, for instance, even for unit disks. But here for general disks, this is possible. And the last problem is, I believe, like everyone's favorite, matching. So finding a matching of the largest number of edges in a given undirected graph. So the recent breakthrough on flow and matching basically says that for bipartite graph, this can be solved in m to the 1 plus small o of 1. For unit disk graphs, this is much faster. So this can be done in n to the 3/2 times log n, which is like improved recently to n to the 4/3 plus epsilon. And there is also 1 plus epsilon approximation for matching in bipartite and non-bipartite intersection graphs of arbitrary disks. So dynamic matching is one of the most well-studied problems in the dynamic graph literature, especially in the last decade. But again, to point out the key difference, they focus on edge updates mainly, and rightfully so because of the degree barrier. If one wants any sublinear update time, so it makes sense to look into the edge model. But in the intersection graph, we can talk about vertex updates. So we are looking into vertex updates. So the question is that can one maintain, let's say, 1 plus epsilon approximate solution for matching for different classes of geometric objects in sublinear update time? So turns out that for disks and fat objects, fat boxes in RD, so there is a dynamic 1 plus epsilon approximate solution with polylog n amortized update time in both the monochromatic and the bichromatic cases. Okay, so to conclude, we obtained a plethora of results on efficient, like static and dynamic approximation algorithms for four classical geometric optimization problems based on simple and general techniques in retrospect, of course, because like we tried many different complex techniques, and it's nice that the simplicity finally worked. And also like the same mechanism has an impact on almost all of these related, also sometimes not so related questions. So the key open problems which remains, which are like strong open questions, is one is that whether there is a constant factor polynomial time algorithm for the minimum piercing set for rectangles in the plane. We only get log log opt. Agarwal et al. Also has like log log opt. Also for constant factor approximation for the weighted version of the maximum independent set for rectangles. Currently, we only have the constant factor for the unweighted version for rectangles. Yeah, and this is for the axis aligned case. Also, this n to the epsilon approximation for maximum independent set for arbitrary line segments or polygons with near linear running time. And another very intriguing and interesting thing is that for axis-aligned segments, we don't know anything better than two-factor approximation, and which is like simply just taking the vertical or the horizontal one. So the question is like, can one beat that? And I guess that like also then finally the question of pitas for independent set of rectangles. And then 2 minus epsilon approximation for the minimum vertex cover of arbitrary line segments or strings with near linear running time. And dynamic algorithms for the weighted version of geometric minimum vertex cover. So with this, I would like to conclude my talk, and thank you for your attention.